Welcome to the lesson on transversals and parallel lines. In this lesson, we will discuss the specific interaction that a transversal has with parallel lines and how we can solve problems with that. Now, a transversal is a straight line that cuts two or more other straight lines. So to show some examples, I could have two random straight lines, not necessarily parallel, and a line that cuts them, and that line acts as a transversal. I can have two lines that are intersecting, and the line that cuts those two lines is a transversal. One of the other lines can actually act as a transversal to the other lines as well. I could have multiple lines. In this case, I'm going to draw four lines. They could be parallel, they could be not, and I'll draw a transversal that cuts across all of those lines. Now, we are specifically interested, however, in a transversal that cuts parallel lines, two lines that do not intersect, and a transversal that crosses both of them, because we will find some very special relationships. To start off, we know that the two angles that are outside the parallel lines and on opposite sides of that transversal are called the alternate exterior angles. Now, if those two angles are on alternate sides of the transversal, but are instead on the inside of those parallel lines, those angles are called alternate interior angles. Now, if I have two non-adjacent angles on the same side of the transversal, with one inside and one outside, they're called corresponding. And all these angles have in common that they are all congruent. All these pairs of angles, wherever you may find them, are congruent to one another. So let's take a look at some examples. Let's apply our practice. I want to find the values of each of these angles in the sketch. Now I do know that these two lines are indeed parallel, and I'm given that one of the angles is 29. So I have to find all the other angles. Well, alternate interior angles would tell me that 6 is 29. Vertical angle theorem would tell me that 7 is also 29. And because 6 and 3 are corresponding, 3 is also 29. Now I got to find the others. I know these two make a linear pair, so if that one's 29, 2 is 151, 1 is 151, 4 and 5 are 151, with a variety of rules and principles to be able to prove their values. But look at the second one. I want to find the measure of angles 1 and 2, knowing that L and K are parallel and D and F are congruent, making an isosceles triangle here. So if the angle down here is 130, E, or DEK, is also 130. And because it's 130, its linear pair would then have to be 50. Now this triangle is isosceles, so the other base angle will also be 50. And now the triangle sum theorem tells me since they're both 50, it adds up to 100. The remaining angle must be 80. So angle 2, its vertical pair has to be 80. So angle 1 was 50, angle 2 was 80, and we were able to use a plethora of rules in order to solve this problem. Now let's get thinking of the converse of this situation. Now the converse of these two theorems states that if two corresponding angles are congruent, then the lines are parallel. So maybe I don't know that the lines are parallel, but let's say I do know these two angles, for example, are both 50. I can go ahead and conclude with confidence that the lines are parallel. So let's take a look at an example and see if I can prove that L and M are parallel, or maybe P and Q are parallel. So let's start off by trying to make some assumptions and see if we can prove something. Now, if these lines are indeed parallel, with this angle being 43, the angle over here to the right, its corresponding pair, should also be 43. Now, if that angle is 43, its linear pair must be 137. Now, 137 doesn't match up with its corresponding pair, so in a sense, L and M are not parallel, and P and Q probably aren't going to be parallel either. But if I take a look at another example, if I take a look at both of these being 145, its linear pair must be 45, and it doesn't match up either.